Hello, welcome to another video lecture for EMA 545. The first thing we're going to talk about today is close natural frequencies. And the theory behind this relies on positive definiteness, which I've defined in the slide here. A matrix is said to be positive definite if this product is greater than 0, or in other words, the dot product between any vector x and itself with the matrix in the middle, or using the matrix as a weighting, is greater than 0. And the reason this is important is that a lot of the matrices that we deal with physically are positive definite. For example, the mass matrix is always positive definite. And the reason for that is if we replace x with q dot or x dot and the matrix with the mass matrix, then this expression is the kinetic energy of the system. And the kinetic energy has to always be greater than 0, no matter what pattern of velocities we apply to the system. Or in other words, no matter which direction those masses are moving, the kinetic energy will always be 0. The same is almost true for the stiffness matrix. It is actually positive semi-definite, which means that this matrix product is always greater than 0, or it can be equal to 0. And I can't remember if we've discussed the case where it's equal to 0 yet. This is a displacement that causes no force, or in other words, if kq for some displacement q gave us a 0, we'd have no force applied to the system. And that happens when we have a rigid body motion. So there's no stiffness force applied to a system for a deformation in a certain mode. Okay, but anyway, because of those properties, when a system with a mass and a stiffness matrix, such as we've used in this class, has two natural frequencies that happen to be equal, or sometimes we say that the natural frequency is repeated. When this happens, the computer, or the process whatever process we use to get the eigenvectors, might give us two eigenvectors that are not orthogonal, because in this case there's kind of an ambiguity about what the eigenvector should even be. It's as if those two modes with equal natural frequencies kind of merge together into one mode, and any piece of those two underlying mode vectors can give us a valid mode for the system. I'll talk about that a little more in a second. But basically, the good thing is that it will always be possible to make those eigenvectors orthogonal and make the system diagonalizable. And the way we do that, I'll describe in a minute. So for the systems we are interested in structural dynamics, it's always possible to come up with a diagonal set of equations and to have orthogonal mode vectors. This isn't true for some other systems. For example, some systems that you might study in controls or systems classes. But here, because we have these positive definiteness properties of M and K and symmetry, this will always hold. Okay, to study this, I'm going to go to an example. Let's see. This is the car that we looked at earlier, and we talked about how to derive the equations of motion for this. And you have a very similar problem in your homework. But in any event, if we take the equations of motion for this system, we found that we have two natural frequencies that are not repeated. But there is a special case where those natural frequencies end up being repeated. Now I'm going to go to some handwritten notes, and these are posted on the course website, so you can look at these. Okay, so here's a schematic of the car, and here I'm going to take a more general case, and this might even be more similar to what you're doing in your homework, but I think you'll still have plenty of work to do to finish that problem. But in any event, the equations of motion for this car, if we say that the inertia of the car, we express that in terms of a radius of gyration and the mass, and we say that the distance between the springs is a over 2, we get a certain mass matrix and a certain stiffness matrix. And there's an expression in here where you can see that the diagonal can go to 0 for a certain value of r over a, or the radius of gyration over the spacing of the springs. For this system, it turns out we can solve analytically for the two natural frequencies, and what we find is that for a certain value of the radius of gyration, we get equal natural frequencies, or if a over r is equal to 2, then the two natural frequencies are equal. And now, what happens when we go to try to find the eigenvectors? Well, remember, we take the equation k minus omega squared m, we plug in omega, which is the natural frequency, and we solve for phi. If we do that, though, in this case, we plug in k minus omega 1, which is equal to omega 2 squared times m, we get a matrix of zeros times phi. Or in other words, phi could be anything and it would still satisfy this equation. So depending on what we choose, for example, if we chose phi 1 to be 1, 0, or where the first end of the car moves and the other end stays still, and we chose phi 2 to be the usual second mode where q1 and q2 are moving in opposite directions, then we calculate phi 1 transpose m phi, we end up getting 1. And this should be 0. These should be orthogonal to each other. So we've lost orthogonality due to this choice of phi 1 and phi 2. But all hope isn't lost. We can choose phi 1 to be anything we want, but now we can also choose phi 2 to be anything that we want. So let's make a choice that causes these eigenvectors to be orthogonal. So I'll call phi 2 just a comma b, and calculate the orthogonality term phi transpose m phi. This should be 0 if the system was orthogonal. And if we multiply this out, so we're setting this equal to 0, and if we multiply this out, we get that a equals 0. So this tells us that if we set a equal to 0, we'll have orthogonal eigenvectors. And now we can choose b to be anything we want. We'll set it to 1, and then we could always mass normalize. So now we have two orthogonal eigenvectors, phi 1 and phi 2. But this has an interesting physical interpretation. What this actually means is that however we displace the system initially, whatever pattern of motion we might give to this car initially, we can call that a mode vector, or an eigenvector, and the system will stay in that shape for all time. It will oscillate at a single frequency in that one shape for all time. And that happens because the displacement as a function of time is the first mode shape times its modal amplitude plus the second mode shape times its modal amplitude. And so we can, if we choose phi 1 such that it captures the initial condition, then this part ends up being 0. And we'll see the system oscillate only in one of its modes. Okay, let's look at some examples to illustrate this. So you'll remember the case we looked at earlier. This is the non-diagonal system. Here we give the car an initial displacement of, I think, this end of the car, a unit displacement, and this end of the car is initially at 0. We'll see that return here in a second. And then we see it oscillating in kind of a chaotic, random way. The center of the car, the point that's at rest, is moving around. We obviously have multi-harmonic motion here. Now, if we look at the case where we excite the system purely in mode 1, this again is the system without repeated natural frequencies. We get the first mode oscillating all by itself. And if we excite the system only in mode 2, we get the second mode oscillating all by itself at a higher frequency. Now we're oscillating at the second natural frequency. So for the standard system, we get two modes with different frequencies, and we have to excite exactly in a mode vector to get a nice harmonic response like this. Let's go to MATLAB though now and look at a case where we have repeated natural frequencies. This script on the course website has repeated frequencies. Now if we run this, we've given an initial condition of Q1 is 1 and Q2 is 0. And you saw this oscillating purely harmonically. So the system stays in the same shape in which we initially deformed it, and it just oscillates a certain number of cycles. And if we change the initial condition now and run this again, we get a different shape, but still a nice harmonic motion of the system. You can maybe see that harmonic motion easier in the time response here. It's just a pure sinusoid. Now, and we can take an even more arbitrary case, run this, and here again we just have a pure harmonic motion. So the mode of the system is anything that we want it to be. Okay, so that's all that I wanted to say about systems with close natural frequencies. We won't worry about them from here on out because we know that we can always choose the eigenvectors to make them orthogonal. And as long as we do that, we can treat modes with equal frequencies the same as we would treat those modes that have distinct natural frequencies. We will just look at a simple model with 3 degrees of freedom. And the goal here is to let you see how we do modal analysis on a 3-degree of freedom system, and to also start to get some intuition about modes. So here we'll model just a single story. We'll model the columns as vertical springs with stiffness K1. The floor mass will break into 3 chunks, and we'll have the floor axial stiffness K2 between those masses. So we could find the equations of motion for this system using power balance. The kinetic energy is easy to see. The potential energy, basically each of these springs, they aren't really drawn in the usual way. Here I'm drawing them as if they were beams. Really it would be a spring attached to ground here and connecting to the mass this way. But in any event, each of these springs K1 just affects the generalized coordinate, its absolute motion, or it exists between that generalized coordinate and ground. The springs K2 are between 2 different masses. And eventually this boils down to this set of equations of motion. Now we could solve this eigenvalue problem by hand, and the rest of these notes show how you could do that. We would take we take the equation k minus omega squared m, we set the determinant of this matrix equal to 0, we get a polynomial in omega squared that we can solve and find the eigenvalues, and I won't go into that anymore, but eventually we find the 3 mode shapes. The first mode shape has 1, 1, 1, so all 3 masses move in sync at the exact same amount. That's sketched down here. The second mode shape is a 1, 0, minus 1, so we have these 2 outer masses moving towards each other and the middle mass standing still. And then the third eigenvector is a 1, minus 2, 1. So here we have the outer masses moving in sync and the inner mass moving opposite of both of those. So that's what we get for this system. And now let's look at how we would do this in MATLAB. And this script is on the course website. So here I have the equations of motion. Oops, I'll take that out. That comes later. Here are the equations of motion. I've set the masses all equal to 1. The springs K1 are a value of 1 and K2 are a value of 2. So this is the floor is twice as stiff as the ground. To be realistic, maybe we need the floors to be 10 or 100 times stiffer, but we'll see what happens there in a minute. And then we can build the mass and stiffness matrices, use the exact same procedure from before. We'll find the eigenvectors and eigenvectors phi and eigenvalues using this command in MATLAB. Find the natural frequencies, which are the square root along the diagonal of this matrix. This lambda matrix is basically free transpose k phi. That's what MATLAB gives you by default. And then the natural frequencies, if we want them in hertz, we divide by 2 pi. And here I did a little bit of sorting. I'm sorting such that the natural frequencies are in ascending order. And sometimes they don't come out that way automatically, and so this is how you would do this with the sort command in MATLAB. And now we can mass normalize them using one of these two formulas. Here I calculate the modal mass between each eigenvector and itself, and then I just divide that eigenvector by the square root of the modal mass, and I have a mass normalized vector. If you're slick with MATLAB, you can do that all in one pop by taking the mode shape matrix and multiplying by this expression. What this is, I'll show you on the notes. Basically, we can take the mode shape matrix, has each of the mode shapes as its columns. If we multiply that by this diagonal matrix that has mu to the minus 1/2 power on it, that will be the same as dividing each of these eigenvectors by the square root of the modal mass. So that's the shortcut way to do that. And now let's run this for a couple of different cases. So first we'll take the baseline case. This is the one we just talked about. The eigenvectors in this case are, well, the eigenvalues are 1, the square root of 3, or 1.73 and 2.64. And those eigenvectors, we have a 1, 1, 1 type eigenvector here, negative 1, 0, 1 here, and this is our 1, minus 2, 1 type eigenvector. These are the mass normalized vectors now. Now let's look at what happens if we start to change this system up. First of all, let's try making that spring, those springs between the floors, stiffer. So we'll go back to this system and we'll make the springs K2 much stiffer than the springs K1. So there's a lot greater force required to move these two masses apart, where all of the masses can move as a rigid body with relatively little force. So to do that in MATLAB, we just change this value to 10. Now it's 10 times larger. And we'll rerun this and see what happens. So here's what we had before. Here's our new answer. The mass matrix was unchanged, but we changed the stiffness matrix. And what happens if you compare the natural frequencies, the first natural frequency didn't change at all. Ask yourself, why did that happen? Why don't you pause the video and see if you can think about why that happened. Okay, you've come back. The reason that happened is that the first mode doesn't involve any relative motion of those masses. So the springs K2 don't matter at all during this first mode. So increasing that stiffness doesn't affect the first natural frequency at all. However, it does drive the second and third natural frequencies up quite a bit because those depend on relative motion between the masses. Okay, one other case that might be interesting. Let's go back to what we had and let's make the spring the mass in the middle 10 times larger and see what that does to everything. So again, the original stiffness, but that spring 10 times larger. And let's see, I'm going to rerun the baseline case so we can compare these two more easily. Okay, so if we run this again, now here we can see, let's see, here's the k equals 2 case with the increased mass, and here's the k equals 2 case with the lower mass. And here, now, with increased mass, we lower all of the natural frequencies except for this second one. Now think about why that doesn't happen. You can pause the video for a second while you think about that. Okay, the answer is, the reason that this natural frequency doesn't change is that that point, the point where we added mass, isn't moving at all in that mode. So that mode of vibration doesn't involve any motion of this mass, so it doesn't matter how much inertia we have there, it won't affect that mode. So that's one interesting observation. And then the other observation is that these other two frequencies have come down quite a bit. Also notice the magnitude of the numbers has changed. We increased mass, And mode shapes have units of 1 over square root of mass, basically. So this made the mode shapes smaller. So mass normalized mode shapes carry the mass there. The other thing that's interesting is this third mode, whereas before we had kind of a 1, 2, 1, 1, negative 2, 1 relationship between the three masses. Now we have the end mass is moving 7 times about as much as the middle mass. So the points on the structure with the most mass tend to want to sit still in the different modes of vibration as we add mass. Okay, so that concludes this online lecture. We've talked about close natural frequencies, and we've talked a little bit about earthquake engineering, and looked at the modes of a simple structure that resembles a building somewhat. It would be very hard to take what we've done and extend that to a multi-story building and take this even farther. Alright, we will see you in class next time.